Welcome to Lecture 10 of Electrical Engineering 525. The first problem for this lecture deals with a V-dipole. And this concept is introduced on pages 212 and 213 of your text. Now, before we jump into the problem, I wanted to call your attention to a couple of points. When you look in your text and read about the V-dipole, look at figure 6-9 carefully, because you will see, if you do that unlike the dipoles that we have been studying up to this point, almost all of which have been collinear with the z-axis, now the V-dipole lies entirely in the xy plane. And it is, you might say, symmetric about the positive y-axis, so that the main beam is in the direction of 90 degrees, or phi equals 90 degrees, or along the direction of the positive y-axis. So do be aware of that change in orientation. Instead of this being along the z-axis, as has been the case with almost all the antennas we've considered up to this point, now this one lies in the xy plane. And note also on page 213 in the third sentence, there's a little typo there, but I want you to be aware of it because it could be a little confusing. If you look in that third sentence on page 213, go to the phrase and lambda from, and change that to and gamma from. And as I say here, this will make more sense to you once we have done this first problem. Okay, so let's go ahead and jump into this first problem. And the first problem is a slightly modified version of problem 6.1-13. I've modified this problem just to make it a little more similar to one of your test problems. So this problem 6.1-13, the modified version of it, reads as follows: to show that the V-dipole results of equations 623 and 624 give roughly the correct results for a full wave straight wire dipole, use D equals 3.82 dB and determine gamma. So what they're giving us here is we have these equations 623 and 624 for the V-dipole, and what we want to do is, if you notice, 624 is for calculating the directivity of the V-dipole in terms of h over lambda, and then 623 is for calculating gamma, which is the opening of the V-dipole in degrees, and that's in terms of h over lambda. So what we're doing, the idea here is that since we have D already, we can use 624, you might say, sort of backwards, and instead of using 624 to calculate D from h over lambda, we can use 624 to calculate h over lambda from D, and then once we have that h over lambda value, we can plug it into equation 623 and get gamma. Now, they're telling us to use the directivity for the full wave straight wire dipole. And so if we do that, the idea is that they're telling us, or they're in this problem, they're hinting that we should expect results that are roughly the same as for the full wave straight wire dipole, since we're using the directivity for the full wave straight wire dipole. So let's see if indeed it will give us values that are roughly the same. So again, then here is equation 624 for the V dipole, and it says that D is equal to 2.95 times h over lambda plus 1.15. Now this formula gives us D, but it's the unitless form of D. It's not in decibels. And so if we want, and see here in the problem, we're given D is equal to 3.82 decibels. So in order to use this formula, we need to first convert it to decibels. And of course, the way to do that then is to, instead of using this unitless form of D, take 10 times the log the base 10 of that value. So in dB, we would have D is equal to 10 log base 10 of 2.95 h over lambda plus 1.15. Now, as we've been told, in dB, the directivity is 3.82. So we plug in on the left-hand side of this equation now. For this is D. Maybe I should actually emphasize that that's the value of D in dB. Okay, so now that makes it more likely that we'll remember the difference. So D in dB is equal to this. So we know that D in dB is equal to 3.82. So we put 3.82 for D on the left-hand side of this equation, and then on the right we just bring everything down. Then we divide both sides of the equation by 10. This is, of course, just pretty simple, straightforward mathematics. So 3.82 divided by 10 is equal to log base 10 of this quantity. And use each side of this equation as the exponent for 10. So we have 10 raised to the 3.82 over 10, or 0.382 power on the left-hand side. And when we take 10 raised to the log base 10 of this, we just get this. So 2.95 h over lambda plus 1.15. Subtract 1.15 from each side of this equation, and then divide by 2.95, and we'll get h over lambda. So if we do this calculation, h over lambda is 10 raised to the 0.382 power minus 1.15 over 2.95. We will get 0.427. Now, for a straight full wave dipole, h over lambda would be 0.5. So we're, as was sort of hinted in the problem, we are not expecting to get exactly the right values, but we're fairly close to the value for the straight full wave dipole here. And in fact, we're going to be even better when we calculate gamma. But here is how h over lambda compares. It's 0.427 using equation 624, but in reality, for the straight full wave dipole, h over lambda would be 0.5. And now to finish this problem, we next want to use, as we've already hinted, we want to use equation 623 to calculate gamma for this situation. Now, in equation 623, it actually comes in two parts. There's two different formulas to use for gamma depending on the value of h over lambda. When h over lambda is between 0.5 and 1.5, we should use this top formula, and when h over lambda is between 1.5 and 3.0, we should use the bottom formula. Now, of course, in the problem under consideration, h over lambda is 0.427, and really that doesn't fit into either one of these ranges, but certainly it's a lot closer to fitting into the top range than it is to fitting into the bottom range. So we will use this top formula to calculate gamma. And so let's just proceed. Gamma is equal to 152 times 0.427 squared minus 388 times 0.427 to the first power plus 324. And if you calculate that, you get 186.04. And again, this is supposed to give you gamma in degrees. So we conclude from this calculation that gamma is 186.04 degrees. Well, for the straight wire full wave dipole, of course, since it's straight, gamma is the opening there would be 180 degrees. So this formula is really giving us really quite an accurate answer for gamma. So you can see then basically the point of this is that equations 623 and 624 do give us pretty good results when we even if we use it in the extreme case of a straight dipole, but of course it's not designed for use in that situation. It's designed; those equations are meant to be used in the case of a V dipole, and that is what you'll actually do in the problem. So, for the first two problems of test 10. So let's go over those problems real quickly and then proceed. So for problem 1 of test 10. You're asked to use exactly this same technique to find h over lambda for a desired value of d equals 6 dB. Now again, in the problem above, we were using the directivity for the straight wire full wave dipole, which is 3.82 dB. But here in this problem, we have a desired directivity of 6 dB. And so with that desired directivity, what is the value of h over lambda? Is it A, 1.64, B, 0.96, C, 1.08, or D, 1.37? And then problem 2 of the test says, using this same technique then, once you have the value of h over lambda, you should find gamma. And what is the value of gamma for this desired value of d equals 6 dB? Is it A, 82.17 degrees, B, 101.61 degrees, C, 91.60 degrees, or D, 77.31 degrees? So those are the first two problems of test 10, and those both deal with the V dipole. So now let's go into section 2 of chapter 6, which moves on from the V dipole now to the folded dipole. And as a problem to illustrate the folded dipole, let's look at problem 6.2-2. There's a little typo in this problem that I want to call your attention to. And it's circled here in red. It says calculate the input impedance of a folded dipole of length, and the first part of the equation says 2a equals L equals 0.4 lambda. That 2a equals should not be there, so just erase that. This equation should simply be L equals 0.4 lambda. The wire size is, this is actually 2a right here. So if you want to put 2a equals something, you could move it over here and say wire size is 2a equals 0.001 lambda. And because of course a is the radius of the wire and 2a is the diameter then. And finally the wire spacing. This is a folded dipole, and so D refers to the spacing of that folding, and D is 12.5A. And so, given all of those values, we're being asked to calculate the input impedance using the transmission line model. and then we will just make a brief comment. Once we've computed that value, we will compare with the results to values from figure 6-16. Now that figure is drawn in such a way that we can't really read it and get a very precise value. So we'll just, once we get the calculated value using these numbers up here, we'll just try to eyeball it and see if it does seem to roughly agree with figure 6-16. So when they tell us to use the transmission line model for the folded dipole, what they mean for us to do is to calculate the two separate impedances, Z sub t for the transmission line mode and Z sub d for the dipole mode or antenna mode, and then use this equation 629, which we'll get to in a moment, to calculate the overall input impedance of the folded dipole from Z sub t and Z sub d in this way. But before we do that, then let's go ahead and look at Z sub t and Z sub d. So as you see in equation 625 in your textbook, Z sub t, and you, I know many of you probably are currently taking microwaves, and so you've probably already run into this equation, that Z sub t for the, this is for a shorted transmission line of length L. The input impedance is J Z naught tangent beta L over 2, where Z naught is the characteristic impedance of the transmission line. And a formula for that is Z naught equals eta over pi natural log of D over A. And eta over pi can be approximated by 120 ohms. And then log of D over A, since D is 12.5A, that just gives us log of 12.5. And if we do this calculation, we get 303.89 ohms. And your book is for the case when D over A is 12.5, as it is in this case, your book is just rounding this 303.89 ohms down to 300 ohms. So since your book is doing that in several cases, we'll do that for this problem as well. So now that we have the characteristic impedance Z naught is equal to 300 ohms, let's substitute that into this equation for the input impedance of the transmission line mode. And when we do that, we get J times 300 ohms for that characteristic impedance times the tangent beta is, of course, 2 pi over lambda. And we're told that L in this case is 0.4 lambda, so we have 0.4 lambda over 2. And when we do this calculation, we will get J 923.3 ohms. So that is the input impedance for the transmission line mode of this problem. And now we need to find the input impedance for the dipole mode or antenna mode. And for this, we don't have a formula. Instead, what we'll do is just now actually we do, if you'll look in earlier in the chapter, we do have an approximate formula, an empirical formula really, for the real part and the input impedance, but not for the imaginary part. So what we will do here instead is just look at figures 6-5 and 6-6, which pertain to exactly the problem under consideration, that is L equals 0.4A and wire size of 0.00, excuse me, it doesn't correspond to L equals 0.40A, that's variable, but it does correspond to the case where D is 12.5A and the wire size is 0.001 lambda. So sorry, I think there was a little unintentional silent portion of the video there. I thought I had hit a button when maybe I hadn't. But anyway, if you look at those figures 6-5 and 6-6, as I was saying, those figures pertain to the case where D is 12.5A and the wire size is 0.001 lambda, or the radius is 0.0005 lambda. And you look in those figures, if you'll move over along the horizontal axis to where L is equal to 0.4 lambda, you will get a value for ZD, the input impedance of the dipole, of 35 minus J170 ohms. So now we have calculated ZT using the transmission line formula. We have approximately estimated ZD using figures 6-5 and 6-6. And so now that we have, let's get this out of the way. Now that we have ZD and ZT, we can use equation 629 in your textbook, which is ZA is equal to 4ZT ZD over ZT plus 2ZD, to calculate the input impedance of this antenna, of this folded dipole antenna. And the only trick about this is obviously just simple algebra. The only trick about it is that, as we've already seen, ZT and ZD are both complex numbers. Actually, ZT is pure imaginary, and ZD has both real and imaginary parts. So you just need to be careful when you do this calculation to not make mistakes because of the complex arithmetic. But if you and so I've shown a step. Here's what the numerator will simplify to. Here's what the denominator will simplify to. And then when we do this division, we get this value here, 345.8 minus J 1034.9. And notice that the units are ohms, because in the top we have ohms times ohms. So we have ohms squared in the top, and the bottom we have ohms plus ohms, so that's just ohms. So ohms squared in the top, ohms in the bottom, gives us overall units of ohms, and which is, of course, is what we expect for the input impedance. So here is the value that we get for the input impedance in this problem. And now the final step, if we look at figure 6-16, and here, as I've already said, we have the same difficulty really that we do in looking at figures 6-5 and 6-6, which is that these figures are drawn in such a way that it's hard to really estimate very precise values. But if you just look at figure 6-16, you would probably come up with a value of somewhere close to 345.8. Now keep in mind, figure 6-16 is only for the real part of the input impedance. But if you do look at that, you'll see that 345.8 does seem to be pretty close to the value that you would estimate from figure 6-16. So that completes that problem, and that leads directly to the last problem on test 10. That's problem 3. And so here you're being asked to repeat this same procedure to find the input impedance of the folded dipole when L is equal to lambda, and assume that all other values are as given above. And so the question specifically, what is the input impedance in ohms? And your choices are A equals 0, B is infinity, C is 300, and D is 50. So those are the choices for this problem. So all three problems, there will be 3 problems for test 10, and on all 3 of them, on the test sheet, only the answers will be shown. So you need to be aware of what the questions are, and of course all of them are embedded in this video. So that concludes the lecture 10, and good luck.